Hello, Geometry Honors. We're starting a chapter over circles. It's not going to be circumference and area and things like that. It's actually going to be a lot of new vocabulary and some aspects of circles that you maybe have never really thought about. And so it's kind of an interesting unit of study. So we'll begin with 10.1, properties of tangents. And like I said, we got some vocabulary today, so let's go ahead and knock this out. We've already talked about the definition of a circle, but let's review that a little bit. A circle is the set of all points in a plane equidistant from a given point. All points in a plane equidistant from a given point called the center. And circles are named by that center point. So down below we see circle C right there. And a segment from the center to any point on a circle is the radius. So yep, from the center to a point on the circle is the radius, and we've used radius for finding area and circumference as well. Now, here's the truly new words, I believe. A secant is a line that intersects a circle in 2 points. And you can see one down here, line BD, that's a secant. Intersects the circle in 2 points. A chord is a segment whose endpoints are on a circle. So a secant contains a chord. You could think of it as segment BD, that would be a chord. And a diameter is a special chord. It's a chord that contains the center. And we've seen diameter in the past as well. We probably more commonly think of it as two radii together back to end, make a diameter. So cutting across the circle, passing through the center. And finally, a tangent is a line in the plane of a circle that intersects the circle exactly once. And you might be thinking that that's kind of a bit of a wordy definition there. Why do they need to have such specificity as far as a line in the plane of the circle? Why couldn't they just say it's a line that intersects the circle in exactly one point, or exactly once. Well, and the reason why we need to think about it that way is if we didn't specify that it was in the plane of the circle, we could have a line passing through the plane three-dimensionally. That would only hit it once as well, but that's not what we're talking about. We're talking about it's in the same plane, hits the circle exactly once. So we've got a tangent here, line AF right there is a tangent. So it's since I've used some of these examples in the picture already, example one should be pretty easy for us. So tell whether the line or segment is best described as a radius, chord, diameter, secant, or tangent of circle C. And we've got DC. That's clearly a radius. Segment BD, since it's a segment, it's going to be a chord. Its endpoints are on the circle. Segment DE. Segment DE is a chord, but it's a special type of chord. Since it passes through the center, it's a diameter. And now they're talking about line AE. Line AE continues through. That touches the circle. It's in the plane of the circle, and it touches it once, and that is a tangent. And finally, line AD, since it's a line that we're talking about that passes through the circle, and passes through the circle twice, that's the definition of a secant. All right, moving on to example 2, use the diagram to find the given lengths. And for part A, it says the radius of circle B. So the radius of circle B, center straight out to an edge. And yeah, it looks like the radius for circle B is 3 units. The diameter of circle A, so 2 points on a circle passing through the center, 4 units. The radius is 2 for circle A. Diameter of circle B, all the way across, passing through the center, 6 units. Okay. Well, some more vocabulary. This is kind of interesting. If you got more than one circle going on, you could have the possibility of a common tangent. A common tangent is a line, ray, or segment that is tangent to 2 coplanar circles. So you got 2 circles, and you got a line that touches each of those circles once. So we've got 2 examples here. Here's a common tangent. See, it's hitting this circle once, and then we got another one below hitting that circle once, that circle once. So yeah, keep in mind tangents, they're hitting at just one precise point. All right, lots of vocabulary. Let's flip it over. Example 3, I like this example. I'm not sure how useful it is in this life that we live, but example 3, I think it's fun. Tell how many common tangents the circles have and draw them. So I like this problem. I'm going to grab a straight edge though to make it a little bit easier. All right, so drawing a common tangent. This is kind of like the example before. I'm going to draw one on top. And it looks like I can draw one on the bottom. And I don't see any other way to do it. You might be thinking, well, you could draw one that hits right there, but it would actually be hitting, yeah, it wouldn't be a tangent, would it? It would be hitting each circle twice. So that's it. We're stuck with the 2. On this next one, though, we got basically 2 circles that are tangent, which is kind of a fascinating idea. We still have the top common tangent. We still have the one below. But since these circles are tangent to each other, there is a single point in here that we could draw a line through and it be tangent to both circles. So it's the rare occasion that you can have a common tangent that only hits one point on a circle, but that point happens to be on 2 circles. So that's a pretty special situation. So we've got 3 going on there. And then on this last one, we've got the typical top common tangents, bottom common tangents. But now with that space in between, we've got something to work with here. I think I could go at an angle here and just catch both triangles. I mean, not triangles, circles. Just catching them both. Ooh, I feel like I drew that about as perfect as it could be drawn. And then, well, maybe not. And then I think I could slant the other way and also get a common tangent in there. Nice. So we actually have 4 different common tangents. Okay, theorem 10.1 says, in a plane, a line is tangent to a circle if and only if, so if you recall that phrase, if and only if, means the statement is true front ways and back ways. Its converse is also true. So we know this is a good definition. So it says, in a plane, a line is a tangent to a circle if and only if the line is perpendicular to a radius of the circle. At its endpoints on the circle. Or end point, I should say. Okay, so basically, if we've got a circle and if we've got a radius out here, if we've got a line that appears to be tangent, we'll know for sure that it's tangent if it makes a right angle with the radius. It's a curious thing. So basically, another way to think about it is if you've got a tangent line on a circle, if you were to draw a radius from that point of intersection to the center, it's always going to form a right angle, which is kind of cool. Another relationship with tangents is this idea here. It's theorem 10.2 says tangent segments from a common external point are congruent. Tangent segments from a common external point are congruent. So we've got a circle. We got some external point. But then from that point, if we were to draw a tangent and a second tangent, well, I kind of overdrew it there. I didn't really mean to extend it out. If we were just to focus on to that point of tangency on one side and the point of tangency to the other side, those segments would have to be congruent. And it's kind of a weird thing because you think, well, no, I'm going to move it this way, then that'll mess it up. But no, you would have new tangent lines, and yeah, they would be congruent as well. No matter where you move that external point, once you draw those tangent lines, they're going to be congruent. Okay, let's put this into action. You're welcome to pause the video, try these yourself, and then check, or you can work them along with me. Example 4 in the diagram, segment AB is a radius of circle A. Is segment BC tangent to circle A? It looks like it is, but it's hard to tell just by appearances. So a way that we've learned to check is that if segment CB is tangent to circle A, it's going to have to form what angle right here? It's going to have to be a right angle because it's going to have to be perpendicular. So how are we going to check to see? Oh, let me put a question mark there because we don't know. We're checking, so we don't know. We're going to put a question mark there, right there. What can we use to figure out if that is in fact a right angle? Well, I'll give you a hint. That 25 radius is also going to be the radius over here, isn't it? That's going to be 25. And we've got a big triangle here. In a previous chapter, I can't remember which one, maybe chapter, I'm not even going to guess, we learned the Pythagorean theorem. Essentially, we used the Pythagorean theorem not just to find a missing side of a triangle, but also to determine what type of triangle it is based off of its angle measures. So what we're going to do is set up the longest side. So the longest side is going to be, you know what, it's hard to tell here if they want that 67 to be in the middle or if they want it to be all the way. I'm guessing that they wanted it to be from, we'll call this point Z right there. I think they wanted 67 to be between Z and C, but it's actually kind of hard to tell where they placed it, but that's the way I'm going to work it out. So we want to do the longest side by itself. So that would be, let's see, 80 plus 13. So 93. That amount squared, oh, I'm sorry, that would be 92. We're going to check and see if that squared, how that relates to the legs, the sum of the legs squared. And I gotta grab my calculator. I'll be honest with you, I worked it out where 67 was the longest side, and we didn't have to use the 25 earlier, but this time when I was working it out, I saw it differently. So I got 8,464, and on the other side, 4,225. Because those are so drastically different, I think maybe it was intended for 67 to be the whole length. On quizzes and assessments and tests, I'll make sure to make that perfectly clear for you. But is this a right angle? No. To be a right angle, these quantities would have to be equal. It turns out that that's an obtuse angle right there, because the 8,464 is greater than the 4,225. So no, it turns out it's not a right angle, and therefore BC is not a tangent to circle A. It is not. It has to be a right angle for BC to be tangent. Example 5. In the diagram, S is a point of tangency. All right, so this one they're telling us straight up that it is a point of tangency. Therefore, it must be making a right angle right here. We don't have to check it. They told us it. And they want us to find the radius of circle T. Well, they drew the radius in both spots. We've got a right triangle. Let's try, I think we probably solve this using Pythagorean theorem. But we do want to be careful here, because our hypotenuse is not just r or 36, it's r plus 36. One of our legs is r, and our long leg is 48. And then to solve this, we've got a lot of r's swimming around here. I'm going to go ahead and simplify this and see if we can't combine some like terms and things. R plus 36 squared is, you would square the front, multiply these together, times it by 2. There's a pattern I'm using here. And then square the back. And so you'd have r squared plus 72r plus 1296 is equal to r squared plus 2,304. And then at this point, if we were to get these r squareds together, they would undo each other. And I've got essentially a two-step equation now. Subtract the 1296 over, divide by 72, and I get r is equal to 14 centimeters. So we kind of lucked out. The r squareds, they eliminated, they went away. And so we didn't have to solve a quadratic. Just to remind you though, had we had a quadratic, we might be able to solve it using square roots. We might be able to solve it by factoring. We might be able to solve it by, we can always solve it by using the quadratic formula. So we may get to do that at some point during this chapter. Example 6, in circle C, segment DA is tangent at A, and DB, segment DB, is tangent at B, and they say to find x. Well, we just learned that if you have an external point and you've got the two tangents to the circle, they're going to have to be the same measure. The sides of that dunce hat are going to have to be the same measure. So we've got a pretty simple equation to write here. and a two-step equation, and I get that x is 5.5. And example 7, is segment AB tangent to circle C? Explain. Well, this is a similar problem, just a little more practice. Do the Pythagorean theorem to check and see what the measure of this angle is. They're very clearly stating here that 34 is segment BC. That's the longest side, so 34 squared. We're going to check and see if that's equivalent to 30 squared plus 16 squared. And I get oh yeah, I get them to be the same, which means this is a right angle. So our answer is yes, because it was a right angle. So class, if you want more practice on this, you can go to page 655, numbers 1, 3 through 10, all, I think that's some vocabulary work. And then 11 through 39 odds is more practice, problem solving. Thanks for watching.